Hello and welcome everyone. Today we're focusing on a project that has not only made significant strides in the field of AI, but also earned a spot in the top 10 projects of Meta AI in 2023. We're talking about SAM, short for Segments Anything Model. SAM is a foundation model for image segmentation. It's equipped with promptable segmentation tasks, robust data annotation capabilities, and a data engine that has collected over 1 billion masks for the dataset SA1B. With SAM, we are exploring new possibilities in image segmentation and masking progress in both computer vision and natural language processing. So join us on this journey as we delve into the workings of SAM and its impact on language models and vision tasks. Let's get started. Imagine a world where language models trained on vast datasets from the web are transforming the way we understand natural language processing. These models, known as foundation models, are like the superheroes of NLP. They have this amazing ability to adapt to tasks and data distributions they've never seen before. Now, you might be wondering, how do they do it? Well, it's all thanks to something called prompt engineering. It's like giving a model a nudge with some carefully crafted text and voila, the model comes up with a valid response for the task at hand. But that's not all. When these models are fed with a feast of text data from the web and scaled up, they start showing some serious muscle. Their performance in zero and few shot scenarios can even match and sometimes outdo models that have been fine-tuned. And the best part, the bigger the model and the more data and computing power it has, the better it gets. It's like watching a superhero get stronger with every challenge. Now, let's take a detour into the world of computer vision. Foundation models have made their mark here too, though not as extensively. Picture this. We have text and images from the web, and we want to align them. That's where models like Clip and Align come into play. They use a method called contrastive learning to train text and image encoders. It's like teaching two different languages to understand each other. Once these models are trained, they can do some pretty cool stuff. For instance, with the help of engineered text prompts, they can generalize to new visual concepts and data distributions they've never seen before. It's like they have a sixth sense for understanding images. But that's not all. These encoders can team up with other modules to perform downstream tasks like generating images. Think of DALL-E, for example. While we've made great strides in vision and language encoders, the world of computer vision is vast and complex. There are many problems out there that we're still trying to solve, and for many of these, we simply don't have enough training data. But hey, that's what makes this field so exciting and full of potential, right? So we've talked about the power of foundation models in NLP and computer vision, but now let's dive into something even more exciting. Let's explore a specific foundation model for image segmentation known as SAM. Image segmentation is a process in computer vision where an image is divided into multiple segments or regions. Each segment represents a specific object or part of the image. It's like giving labels to pixels that belong to the same object. This technique is crucial in many applications, including object detection, facial recognition, and self-driving cars. I used Bing's ability to make this original image of this girl. I then turned to Sam's demo and segmented the image using three distinct options: the everything option, the hover and click, and the box option. In the upcoming slide, we'll unravel the mysteries of SAM. We'll answer some burning questions like what task enables it to generalize on zero-shot basis? What's the architecture of this model, and what kind of data fuels this task and model? We'll discover how a promptable segmentation task can open up a world of downstream applications. We'll see how the model's architecture supports flexible prompting and real-time output of segmentation masks. And we'll learn about the diverse large-scale data that powers this model and the unique data engine they've built to overcome the lack of web-scale data sources for segmentation. The Segment Anything project is made up of three closely linked components. First up, we have a segmentation task that's promptable. It's like a chameleon adapting to whatever you need it to do. Next, we have the star of the show, the Segment Anything model, or SAM for short. It's the powerhouse that drives data annotation, and with a little help from prompt engineering, it can transfer its skills to a variety of tasks without any prior training. Last but not least, we have our data engine. It's like a treasure hunter, tirelessly collecting SA1B, the dataset for segmentation that boasts over 1 billion masks. Together, these three components form the backbone of the Segment Anything project, each playing a crucial role in its functionality. Building on what we've discussed, let's delve into the concept of the segmentation task. The segmentation task is essentially about taking an image and a prompt and using a model to generate a valid mask. It's a key process in computer vision that allows us to focus on specific parts of an image based on the prompt. This task plays a crucial role in pre-training and solving a variety of segmentation tasks. Now, you might be wondering what exactly is a prompt. Well, a prompt simply specifies what to segment in an image. It could be a set of foreground or background points, a rough box or mask, freeform text, or any information indicating what to segment in an image. It's like giving a hint or clue to the model. But there's a catch. The prompt can sometimes be ambiguous. For instance, a point on a shirt could indicate either the shirt or the person wearing it. Despite this ambiguity, the model is expected to return a valid mask. This means the output should be a reasonable mask for at least one of those objects. It's similar to expecting language model to output a coherent response to an ambiguous prompt. This task is chosen because it leads to a general method for zero-shot transfer to downstream segmentation tasks via prompting and a natural pre-training algorithm. The pre-training algorithm involves simulating a sequence of prompts for each training sample. These prompts could be anything: points, boxes, or masks. The model then takes these prompts and makes predictions for the segmentation masks. These predicted masks are then compared against the actual or ground truth masks. This process helps the model learn and improve its ability to generate accurate segmentation masks for prompts. Now, let's take a look at the model's internal architecture. The design of this model is influenced by the requirements of the promptable segmentation task and the goal of real-world application. This model needs to be flexible enough to handle different prompts, compute masks in real time for interactive use, and be aware of any ambiguities. Surprisingly, a simple design manages to meet all these requirements. The model, which we call the Segment Anything model or SAM, consists of a powerful image encoder that computes an image embedding, a prompt encoder that embeds prompts, and a lightweight mask decoder that combines these two sources of information to predict segmentation masks. By separating SAM into an image encoder and a fast prompt encoder mask decoder, the same image embedding can be reused with different prompts, making the process more efficient. Once an image embedding is given, the prompt encoder and mask decoder can predict the mask from a prompt in just 50 milliseconds on a web browser on the CPU. To handle ambiguity, SAM is designed to predict multiple masks for a single prompt. This allows SAM to naturally handle ambiguous situations like this shirt versus person example we discussed earlier. So, as you can see, SAM is not just a model. It's a carefully designed tool that's pushing the boundaries of image segmentation. Let's now turn our attention to the image encoder, a key component of SAM. This part of the model is motivated by the need for scalability and the power of pre-training models. A vision transformer is used that's been pre-trained using MAE. This vision transformer has been minimally adapted to process high-resolution inputs. Since the goal is to process each prompt in real time, we can afford a high computational cost for the image encoder as it runs only once per image, not per prompt. We follow standard practices for the input resolution using a resolution of 1024 by 1024 obtained by rescaling the image and padding the shorter side. This results in an image embedding of 64 by 64. Now let's shift our focus to the prompt encoder, another integral part of SAM. The prompt encoder deals with two types of prompts: sparse prompts, which include points, box, and text, and dense prompts, which are essentially masks. Sparse prompts are transformed into 256-dimensional vectorial embeddings. For instance, a point is represented by a positional encoding of its location combined with one of two learned embeddings that indicate whether the point is in the foreground or background. A box, on the other hand, is represented by an embedding pair that includes the positional encoding of its top left corner and bottom right corner, each combined with a learned embedding. Freeform text prompts are handled using a text encoder from Clip. The prompt encoder plays a crucial role in handling different types of prompts and transforming them into a form that the model can work with. It's like the model's own language translator, converting prompts into a language that the model understands. Now, let's turn our attention to the mask decoder. This component is like the conductor of an orchestra, efficiently mapping the image embedding and prompt embedding to a mask. The design of the mask decoder is inspired by previous works and employs a modified version of a transformer decoder block. This follows by a dynamic mask prediction head, which is like the grand finale of a fireworks show. The modified decoder block uses self-attention and cross-attention in two directions, from the prompt to the image embedding and vice versa. This process updates all embeddings, ensuring they're in sync. After running two blocks, the image embedding is upsampled. An MLP then maps the output token to a dynamic linear classifier. This classifier then computes the probability of each image location being on the foreground of the mask. So, as you can see, the mask decoder plays a crucial role in the model, ensuring that the final output mask is accurate and meaningful. Let's now explore how SAM handles ambiguity. When given an ambiguous prompt, a model with a single output will average multiple valid masks. To tackle this, SAM is tweaked to predict multiple output masks for a single prompt. It's found that 3 mask outputs are usually enough to cover most cases, such as nested masks that are often 3 layers deep: whole, part, and subpart. During training, only the minimum loss backpropagates over mask. This is a common technique used for models with multiple outputs. To rank masks, the model predicts a confidence score for each mask, estimating the intersection over union between each predicted mask and the object it covers. Now, you might be wondering what happens when there are multiple prompts. Well, ambiguity becomes much rarer and the 3 output masks usually become similar. To minimize computation and ensure the single unambiguous mask receives a regular gradient signal, only a single mask is predicted when more than one prompt is given. This is achieved by adding a fourth output token for an additional mask prediction. This fourth mask is never returned for a single prompt and is the only mask returned for multiple prompts. So as you can see, SAM has been carefully designed to handle ambiguity, making it a robust and versatile tool for image segmentation. Lastly, we know that this level of generalization needs lots and lots of data. To achieve this, SAM was trained on a large and diverse set of masks, surpassing any existing segmentation dataset. But here's the challenge. Masks are not naturally abundant, so we need an alternative strategy. The solution? A data engine. This data engine is a three-stage process that co-develops the model with the model-in-loop dataset annotation. It starts with the assisted manual stage. A group of skilled annotators worked with SAM to label masks. They used a browser-based interactive segmentation tool powered by SAM and identified foreground and background objects by clicking on specific points. To refine these masks, they used precise brush and eraser tool. There were no restriction on what they could label, giving them the freedom to label both stuff and things. This stage was all about collaboration and precision. Then we move to semi-automatic stage. Now imagine SAM stepping up its game. It starts to automatically generate masks for certain objects, while the annotators focus on the remaining objects. Finally, we reach the fully automatic stage where SAM runs solo. It's now capable of generating high-quality masks by itself, using a grid of points as prompts. It's like watching a skilled artist at work, effortlessly creating masterpiece after masterpiece. This process led to the creation of the 1.1 billion mask dataset SA1B. And that brings us to the end of our deep dive into SAM, the Segment Anything model. SAM is not just a model, it's a testament to the power of AI and its potential to revolutionize both computer vision and natural language processing. As we continue to explore and push the boundaries of what's possible with AI, models like SAM light the way, showing us what can be achieved when we dare to imagine. Thank you for joining us on this journey. If you found this video informative and want to learn more about the fascinating world of AI, don't forget to like, share, and subscribe. Until next time, keep exploring, keep learning, and remember, the future of AI is here and it's more exciting than ever.